Okay, welcome everybody. I'm Ted Porter, and I'm chairing the session. And I was sternly advised to do what I can to make this move quickly, which means not to give extended introductions. And so I decided to save my brilliant witticisms, which I couldn't really keep up with John Heilbronn. Anyway, for the 80th birthday or the 90th birthday, so I'm looking forward to that, and I'll be gathering up the ones I hear so that I can use them next time after the rest of you have all forgotten them. So we have four speakers in this session, and I hope they can carry out give their talks in 15 minutes or so, and we'll try to keep on time and have a little time for discussion. So there they are. They can introduce themselves. We start with Craig Fraser from the Institute for History of Science and Technology in Toronto. So,
one of the things I've been working on lately involves original sources and some issues that arise in original sources, and I thought I'd work this theme into something that connected my background to Jed Buchwald, and just talk about some aspects of using original sources in the history of mathematics and the history of science more broadly. So this is basically going to be a trip down memory lane, but I want to just mention that this topic of original sources is a fairly ongoing one right now. So the National Science Foundation is funding an ongoing project called TRIUMPS. TRIUMPS stands for Translating Undergraduate Mathematics via Primary Historical Sources, which is intended to engage students with mathematics by looking at original sources. And the people that are doing this have produced some fairly interesting case studies. Another example of this current interest, and I'll put in a plug for a book of my co-panelist, Jeremy Gray. So the course on the history of mathematics that is focused on original sources in translation is in press and will be coming out, and it is authored by Jeremy Gray, June Barrow Green, and Robin Wilson. So recently I've been doing research on the history of Hamilton-Jacobi theory around 1900, particularly looking at the development of something called the theory of canonical transformations. I've been struck by how little German quantum physicists who sometimes made historical remarks seem to have read the actual writings of Jacobi. Although Jacobi died in 1851, his lectures on dynamics were published in 1866, and his collected work was published between 1881 and 1891. The physicists had also not read anything by William Rowan Hamilton, but that is perhaps more understandable. So this is really why I was thinking about original sources in this current work I'm doing when I decided to work up something for this conference. So I want to talk about my first exposure to original sources in the history of science, and we'll rev up the time machine now and go back in the past. The first course I took in my graduate studies in the history of science was with Jed Buchwald in 1976 at the University of Toronto. We looked at the history of physics from Galileo to Maxwell and Boltzmann. So I had come from basically a background of doing nothing but mathematics, and this was really my first exposure to the history of science. One of the things that was drilled into us at IHPST at this time was the importance of staying in close touch with the original texts. Students were required to demonstrate proficiency in reading French and German and to have a working knowledge of whatever languages were required for their historical work. So, I ended up not really realizing this, that I was going to have to do this, spending, basically thousands of hours studying languages over the years. This is a quote from Noel Swerdlow in a book in a review he wrote of Robert Newton's The Crime of Ptolemy Almagest, and it refers to Ptolemy's Almagest, but it could refer to any older text in the history of science. Unlike literature and the arts, which possess a kind of immortality and can for the most part speak to anyone who makes the trouble to examine them with care and sensitivity, earlier science is mostly dead and mostly technical, requiring various kinds of prior knowledge just to be intelligible. Moreover, in the course of their development, the sciences have undergone changes so great that in many cases neither the methods nor even the subject matter of earlier science is self-explanatory to the reader who is familiar with contemporary science. Whatever becomes obsolete eventually becomes unintelligible, and consequently the living memory of the sciences seldom extends back more than a couple of generations. So this is a sort of statement of the general problem of reading an older technical source in past science. Now, a historian of mathematics named Harold Edwards, or Ed Edwards, has advocated that mathematicians should read original sources, and they gain great benefit from reading these. This is he wrote an article called Read the Masters, and this is a quote where Swerdlow kind of echoes some of the things that Edwards echoes some of the things that Swerdlow said about the difficulties of grappling with original sources. To read the classics in mathematics is not as easy as it might sound. Changes in terminology and style and in the general mathematical milieu make mathematics, regarded ironically by the man on the street as an immutable body of facts, a field in which works written only a decade or two ago often sound archaic to young readers. The first topic we considered in Jed's seminar was Galileo's account of dynamics on day 3 and 4 of 2 New Sciences. Now, I'm 100% certain that I took this topic with Noel Swerdlow in a seminar he gave. I'm 80% certain I also took it with Jed, and I took a course with Stillman Drake on the history of proportion theory, and I think that I got this topic with him as well. So the example is the law of falling body, which Galileo presents on day 3 of his 1638 book, Discourse on 2 New Sciences. And it is the standard elementary problem that we get in entry-level physics, involving a differential equation expressing the relationship between the acceleration and the force, the initial condition. We integrate this simple differential equation to get dx dt equals gt, and then finally we get that x is equal to 1/2 gt squared, or the distance fallen is proportional to the square of the time. So this is the modern example, and then we looked at this in Galileo's original treatise. So it was given by Galileo's book was written in Italian, but the particular section where he presented his theory of falling bodies was done in Latin. And this is the work, which was the second of his 2 major works, the earlier one being the Dialogue on 2 World Systems. The 2 New Sciences are the motion of bodies and the strength of materials. And this is the proposition theorem 2 of day 3, where Galileo deals with the motion of a falling body and derives the law that the distance fallen is proportional to the square of the time. Galileo's book was translated into English just about 25 years after it was published, rather unusual for books to be translated into these major classics to be translated into English. I think the reason for this must have been that it was written in Italian. If it had been written in Latin, it wouldn't have been translated. Gilbert's De Magneta was not translated from Latin into English for 300 years. And Salisbury says that he Englished the original Latin and Italian. So the Latin is the subpart of the work where he presents his work on motion. And then the actual book we used in the seminar was Stillman Drake's translation, which was published in 1974. So it was fairly hot off the presses, and it was a kind of a better translation than Salisbury's 17th century translation. Galileo's original result was in a Latin treatise contained within a larger Italian work. There's no algebra or formulas, there's no calculus, and the underlying physics is antiquated. In order to follow Galileo's treatment in its original form, it is necessary to have some knowledge of Italian and Latin, So ultimately, if you're going to do original historical work, it's necessary to work with the original text rather than with translations, clearly. It's also necessary to understand a little bit about some parts of the history of mathematics. In particular, Galileo doesn't present things using algebraic formulas as we do today. He was still working within a kind of classical Euclidean terminology of proportions and ratios. And he was also working with various elaborations of this theory that had occurred during the Middle Ages. So to kind of grapple with the way that Galileo presents the material, it's necessary to know something about Euclidean proportion theory and its medieval developments of the theory. Another thing that Galileo evokes in his demonstrations is references to indivisible lines in figures, and he is sort of echoing certain notions that were developed much more systematically by his contemporary Cavalieri, who published a book in the 1630s about using the method of indivisibles in order to find areas and volumes. It was a kind of treatise on what we would today call the integral calculus. So it's necessary to know a little bit about that whole kind of part of mathematics where they were trying to find integrals, areas, and volumes. And finally, an important part of the background to this proposition is the whole stream of thinking in medieval impetus theory. So medieval impetus theory, which was created in the 14th century, was a kind of halfway house between Aristotelian physics and modern inertial physics. Galileo is one of the heroes in the creation of modern inertial physics, but he's still working from this background of medieval impetus theory. In comparison to other early modern scientists, Galileo was notable for the lucidity and accessibility of his writing. Even in the case of Galileo, there are challenges in attempting to appreciate familiar results in their original setting. I'm quoting here from a review that Jed wrote of a book by Clifford Truesdell, who founded the journal, The Archive for History of Exact Sciences, and Jed took over the editorship of this journal from Clifford Truesdell. Clifford Truesdell was a major figure in the middle of the 20th century in the history of exact science. In many respects, he was a kind of complicated figure. He did some extremely impressive, even monumental work on the history of mechanics and thermodynamics. But he was also someone that had very strong opinions and always didn't fit in with the contemporary currents in the field, particularly as they were developing in the 1960s and the 1970s. This is a book, I think the title of the book was An Idiot's Fugitive Essay on Science, or something like that. And Truesdell being the idiot in the title, but used. So anyways, this is what Jed writes about this book, and I think his remarks are very much apropos. Truesdell's historical essays form a logical part of the insistence on proper understanding of the primary sources that became common in the history of science by the early 1950s. Nearly every page on his Histories of Mechanics bears witness to his insistence on careful reading and explaining the original material and not inserting into it concepts that were developed much later. So in this review, Jed emphasized the challenges and rewards of understanding the intrinsic technical content of past mathematical science in its original historical setting, something that can often be a challenging project. This was an important lesson I learned in Jed Buchwald's seminar in the history of physics in the late 1970s. This lesson was also conveyed in the graduate teachings of other IHPST faculty during this period, and I'll only mention people I took courses with, and that were Trevor Levere, Stillman Drake, Kenneth May, and visiting Professor Noel Swerdlow. And I might add to that list Polly Windsor, who's here today, although I didn't actually take any courses with Polly, so I can't speak from firsthand about that. So this is my memoir, Jed, for the presentation today related to mathematics. Thank you.